Hello students, welcome to physics class. Today we starting a new chapter in physics, that is mechanical properties of solid. Chapter 9 from NCERT textbook. You know that solid is one of the state of matter which has a proper shape and size. When you are comparing to other states of matter like liquid and gas, you know that liquid and gas have no particular shape. Gas have no particular size. So, comparing to these states of matter, the solid has a definite shape and size. But the shape and size of the solid can change by applying an external force. With the help of an external force, we can change the size and shape of this solid. And so, such an external force which can change the size and shape of the body, of a solid body, are known as deforming force. You know that when you are applying a deforming force, we can change the shape of the solid. For example, suppose if you have a helical spring. If you are applying a force on this helical spring to extend its length, we can increase the length of the spring. Spring is a solid, so the size of the spring is changed, or size of the solid is changed by applying a deforming force. So a deforming force is nothing but a force which changes the size or shape of a body is called a deforming force. So by applying an external force, we can change the size and shape of the body, and such an external force can be called as a deforming force. So you know that once you are applying a deforming force on an object, the object's configurations are changing. So if a body regain its original size and shape after the removal of this deforming force, it is said to be an elastic body, and this property is called elasticity. Some of the solid showing this property of elasticity, that is, if you are applying a deforming force, the size and shape of the body is changed. If a body regains its original size and shape after removal of deforming force, it is said to be elastic body, and this property is called elasticity. Most of the solid showing this phenomenon of elasticity. Once you are removing the deforming force, the objects or that solid comes to the initial configurations. So we can say such body as elastic body, and that phenomenon is known as elasticity. In some solid, they're showing the perfect elasticity. That is, just after the removal of deforming force, quickly they come to the initial configuration. Completely it gains its initial configuration, size and shape. Such body or such solid are generally known as perfectly elastic bodies. Perfectly elastic body. They completely gain the original configuration soon after the removal of deforming force. For example, quartz fibers are perfectly elastic bodies. Soon after the removal of deforming force, they come to the original configurations. So perfectly elastic body. So most of other solid showing elasticity, that they can come to the original configuration after the removal of deforming force. Now let us see what is plasticity. Some solid are not showing or not regaining the original configurations even after the removal of the deforming force. Such bodies are known as such bodies are known as plastic bodies, and that phenomenon is known as plasticity. That is, if a body does not regain its original size and shape even after the removal of deforming force, it is said to be plastic body, and this property is called plasticity. If a body does not regain its original size and shape even after the removal of deforming force, it is said to be plastic body, and this property is called plasticity. Some solid showing this phenomenon of plasticity. For example, the paraffin wax and putty. They are perfectly plastic material. It means that they never regain their original configuration or original size and shape even after the removal of deforming force. So such bodies are known as perfectly plastic body. For example, paraffin bags and putty are perfectly plastic body. They never regain the original configuration even after the removal of deforming force. So we learned that the size and shape of the solid can be changed. Even though the solid are rigid, the size and shape of the solid can be changed by applying an external force. Such a force is known as deforming force. And the solid can be classified into elastic material and plastic material. Elastic body and plastic body. Elastic bodies are the solid which can regain the original size and shape even after the removal of the deforming force. Whereas the plastic bodies are the solid which cannot regain or which do not regain the original size and shape even after the removal of deforming force. They are known as plastic material or plastic bodies. Once you are applying a deforming force on a solid, inside the solid, at each and every part of this body, an opposing force is originating. Just opposite direction of this deforming force, an opposing force is originating to regain the original configurations. To regain the original configuration, an opposite reaction is originating inside the solid. And that force is known as the restoring force. Restoring force is a force which originating inside the solid against this deforming force. So suppose if you are applying a deforming force on a body, the restoring force set up per unit area cross section of deformed body is called stress. The physical quantity stress is defined like this way. The internal restoring force set up per unit area of cross section of deformed body is called stress. So stress is equal to applied force by area. We know that the restoring force is numerically equal to the applied force by Newton's third law, and equal and opposite force is originating inside the solid. So we calling that as a restoring force. So restoring force is numerically equal to applied force. So the stress is equal to either the restoring force by area or applied force by area. Suppose if F force is acting on a body having an area A, then we can say the stress is equal to force by area, F by A. The SI unit of stress is Newton per meter square. And its dimension is M L raised to minus 1 T raised to minus 2. That's the dimension of the stress. So stress is the applied force by area or the restoring force by area. The restoring force developed per unit area cross section is known as stress. Now there are different type of stress because we can apply the deforming force in different way. So the stress is also in different type. Let us see different type of stress. First one is a tensile stress. Tensile stress. Suppose we have a road like this having an area A and length L. And suppose here we are applying a force to increase the length of this road. So here we are applying the force in both direction along the length of this road. So usually its length will increases. So by the time the force per unit area, if F is the applied force, force per unit area developed here is known as the tensile stress. Tensile stress. Suppose the applied force, that is deforming force, is trying to increase the length of the rod or length of the string, then force per unit area is known as the tensile stress. Suppose if you are applying the force from both sides of this rod to decrease the length or to compress this rod, then the stress is originating here. That is force applied force per unit area in this time is known as compressional stress. Compressional stress. And suppose a uniform force is acting from all direction on a body to reduce its volume, the stress originating by this time is known as hydrostatic stress. The hydrostatic stress, that is, if a uniform force is acting on this body from all direction to reduce its volume or to change the volume of this body. So a stress is originating by this time, and such a stress are known as the hydrostatic stress. And suppose a force is acting on a solid object along the tangent of a surface, such a force will change the shape of the body. So by the time the stress acting on this object is known as tangential stress or shearing stress. So there are the different type of stress. One is a tensile stress, compressional stress, hydrostatic stress, and tangential or shearing stress. That are the different type of stress which can act on a body when it is deforming. Now let us see. Once you are applying a stress on a body, it gets strained. Let us see what is strain on a body. The strain is defined like this way. The ratio of change in any dimension produced in the body to the original dimension is called strains. You know that once a deforming force is acted on a body, the size and shape of the body will change. So, the ratio of change in any dimension produced in the body to the original dimension is called strain. So, strain is equal to change in dimension by original dimension. Change in dimension by original dimension. So it's the ratio of two similar quantity. So there is no unit and dimension for the strain. Strain have no unit and dimension. It is a ratio of change in dimension by original dimension. The ratio of two same quantity. So there is no unit and dimension for strain. Now let us see what are the different types of strains. Longitudinal strain. The longitudinal strain. It is defined as the increase in length per unit original length when the body is deformed by an external force. It is defined as the increase in length per unit original length when the body is deformed by external force. For example, suppose here we have a rod of length L and area cross section A. In order to deform this rod, a force F is acting. So the length of the rod is changed. Suppose there is an increase of length delta L. So the strain is the change in length by original length, delta L by L. So that is known as longitudinal strain. The change in length by original length is known as longitudinal strain. Now see volume strain. It is defined as the change in volume per unit original volume when the body is deformed by an external force. For example, suppose if you have a spherical body of volume V which is immersed in a fluid, so now that the uniform force is acting or uniform stress is acting from all direction, so the volume of the body will change. Suppose there is a change in volume delta V, there is a decrease in volume for that body. Delta V is the decrease in volume. So we can write the volume strain is equal to change in volume by original volume. So delta V by V is known as volume strain. Shear strain. The third one is shear strain. It is defined as the angle theta through which a face originally perpendicular to the fixed face get turned on applying a tangential deforming force. For that, suppose here we have a cubical body and on this face tangentially we are applying a force. A tangential force is acting on that face. The face having an area A. So what happened? This face which was originally perpendicular turned through an angle theta. Now this is after applying the force, this is the position of that plane. This is the original position, but by applying an external force tangentially on this face, the originally perpendicular face get turned through a very small angle, let us say theta. So that is known as the angle theta through which a face originally perpendicular to the fixed face get turned on applying tangential deforming force is known as shear strain. So here in this diagram we can write tan theta. Tan theta is equal to here opposite side, that is delta L. This is the change in length, or this is the original position of this face, and it is displaced by a very small distance, delta L. So delta L by L, that is tan theta. You know that tan theta, if the angle is too small, tan theta is approximately, we can write as theta. Theta is equal to delta L by L. That is known as shear strain. Shear strain is the angle theta through which a face originally perpendicular to the fixed face gets turned on applying a tangential deforming force. So tan theta is equal to delta L by L. Theta is too small as it is a solid body, solid rigid body. So theta is equal to delta L by L. We cannot apply a large stress on a body. If you are applying a huge stress on a body, the body will permanently change its configurations. The body cannot regain its original configuration even after the removal of deforming force. Then, for every body, there is a limiting value of stress that we are calling as elastic limit. The maximum stress within which the body regain its original size and shape after removal of deforming force is called elastic limit. If you are exceeding the elastic limit, if you are increasing the stress beyond that value, the body will change its shape permanently. The body cannot regain its original configuration even after the removal of the deforming force. Once you know that, if you are extending a spring by applying a huge force, if it elastic limit exceeds, it cannot come to the original configuration. Permanently, the length of the spring will change. Now see, one of the very important law related to the stress and strain, that is related to the elasticity of a material, is known as Hoax Law. According to Hoax Law, within elastic limit, the stress is directly proportional to strain. According to Hooke's law, within elastic limit, the stress is directly proportional to strain, or stress is directly proportional to strain, or stress is equal to a constant of proportionality into strain. The stress is equal to a constant into strain. Or you can rewrite like this way: stress by strain is a constant. Stress by strain is a constant. And this constant is known as modulus of elasticity. Modulus of elasticity, or coefficient of elasticity. If you are plotting a graph between the stress and strain, you know that whenever the stress increases, the strain on the body is also increases. Here the stress is taken on y-axis, strain is taken on x-axis. So it shows that when the stress is increases, the strain is also increases. The stress is directly proportional to strain. So the slope of this graph actually gives the modulus of elasticity, because the slope of this graph is equal to stress by strain. So it gives the modulus of elasticity. So modulus of elasticity is defined like this way. The modulus of elasticity is defined as the ratio of the stress to the corresponding strain within the elastic limit. The modulus of elasticity is defined as the ratio of the stress to the corresponding strain within the elastic limit. So modulus of elasticity is equal to stress by strain, and its unit is Newton per meter square, because the strain have no unit. So the unit of modulus of elasticity is the unit of stress. That's why it's become Newton per meter square, and its dimension is m l raised to minus 1 t raised to minus 2. Now let us see the stress strain curve for a metallic wire. So in order to study the relation between the stress and strain for a metallic wire, here we have a metallic wire of length L and area cross section A. It is being loaded. Here we are suspending some weight, and we can increase the weight by adding more and more. So once we are hanging some weight from this, actually we are applying a tangential stress. Actually we are applying a tensile stress on this string. So once a tensile stress is acting on the string, it will produce a longitudinal string. So we are trying to plot a graph between the tensile stress and the strain acting on the string. So initially, if you are increasing the weight on this string, we are increasing the stress gradually. We can observe that when the stress increases, the strain also increases. Whenever the stress increases, strain is also gradually increases. So we are getting a straight line between the stress and strain. If you are plotting a graph between the stress and strain by taking the strain on x-axis and stress on y-axis, up to the point A, whenever we are increasing the stress, the strain also increases. In order to increase the stress, what you are doing is we are adding more and more weight. So stress increases, strain also increases. So in this graph, OA is a straight line. It means up to the point A in this graph, it obeys the Hooke's law. The stress is directly proportional to strain. So the point A is known as proportional limit. Up to the point A only, the stress is directly proportional to strain. After that, suppose if you are increasing the stress beyond to the value of A, the strain increases, but they are not directly proportional. It means there is a large strain even for a small stress. So it is not a straight line from the point A to B. But from O to B, whenever we are removing the stress, the strain comes to zero, or the string comes to the original configuration. The removing the stress means we are removing the weight. Once we are removing the weight, the string comes to the original configuration or original length. The string can regain its original length. So up to the point B, the object or our string showing the elasticity or elastic behavior. So the point B is known as elastic limit. If you are increasing the stress beyond that value B, the body cannot regain its original length even after the removal of this force. Even after the removal of the stress, the body or the string cannot regain the original configurations. So that the point B is known as elastic limit. Up to the point B, it can regain the original length. Beyond that B, we cannot regain the original configuration. So the curve, the part of this curve OB is known as elastic behavior. Up to the point B, it's showing the elastic behavior. Means the string can come to the original length even if you are removing the stress. Suppose if you are again adding this weight on the string, we are increasing the stress. So once the stress increases, strain also increases, but they are not directly proportional. There is a large increase of strain for a small increase of stress. So from B to C, again we are getting not a straight line, we are getting some curves. But if you are removing from B to C, if you are removing the stress, that is, if you are removing this weight which is hanging from the string, we cannot regain the original length of the string. Permanently, the length of the string is changed. So from the point, suppose from the point C, if you are removing all the weight which is suspended from the string, the length of the string is not comes to the original length. Even after the removal of the stress, you can see that in the diagram, the stress comes to zero, but the strain is not comes to zero. There is a little bit of strain which is remain in this string. That is, length of the string is permanently changed. So this value OE, which is a residual strain in the string, even after the stress comes to zero. And this value we calling as permanent set because it is a permanent change in the length of the string. So this we calling as permanent set. Suppose if you are going the adding the weight, if you are continuing the weight adding, what happened is that the stress increases considerably, the stress increases, and at finally if you are increasing the weight again and again, the string will break. And so we calling as there is a huge increase of strain, even there is a very small increase of stress. So we can say at this point the strain increases largely, and what happened is that the string is break, and this point we calling as fracture point. So from the C to D, it's showing a plastic behavior because even if you are removing the stress, the string cannot come to the original configuration. So this region of this graph C to D is known as plastic behavior. So this is the graph between the stress and strain for a object solid or a solid string which is loaded. That's all today. Thank you.